concepts of calculus, of differential calculus that is, and we'll be starting integration in today's lecture. But of course, the assignment I gave you, the last one, had some pretty lengthy type of questions and tricky type of questions. So I'll be discussing some of them in class today. Then I'll be sending you the answer key and hints after that. And the remaining ones, you can, if you still have any doubts, you can try and figure out from the hints. If not, then we will discuss again. And at that point of time, we will start with integration. So let's begin. So we'll start with the discussion of some questions from worksheet number 5. So I'm going to start with question number 1, part. Just a moment. Yeah, question number 1. Let's do part 1. You want to find the domain and range. So what I want to show you in such type of question is that you don't always have to use calculus and maxima and minima. For domain and range, we can go with a sort of logical method, especially in this type of question. So here, for example, for domain, what we can see is that y is real for all x such that the quantity inside the square root, that is 1 minus 2 sine x, should be greater than equal to 0, which means that sine x should be less than equal to half. So that basically means that sine x should range between -1 and half. Okay. So now to understand what values of x are over here, next what you can do is you can look at you can recall the graph of sine x. Okay, and understand for which values sine x goes greater than half. Okay, so if you look at the fundamental graph of sine x in one cycle only, 0 to 2 pi, that will be enough to figure out for the sort of global range of sine x what is happening. So in one cycle, sine x goes from 0 to 1, then comes back from 1 to 0, and goes to -1, and comes back like this. So in this, we have to figure out this part, okay, where it goes beyond half. So we want to remove that part from the domain. The rest of it is fine because, so basically we want to, so if this is the graph of y equal to sine x, we want to remove that part of the domain where this is happening, where we don't want this part. Okay, we are fine with this part, this part. Because we want this, that x should be less than equal to, I mean sine x should be less than equal to half. So you can see from this that this point here is 30 degrees or pi by 6, and this point here is 150 degrees or 5 pi by 6. So we have to remove this part of the domain. Rest of the values are fine. So this is showing us here that x's values in the fundamental domain between 0 to 2 pi, x is okay between 0 and pi by 6, but then we should remove the part between pi by 6 and 5 pi by 6 and take the rest of it again. So this is in 0 to 2 pi. Okay, so general solution will become that x belongs to 2n pi to 2n pi plus pi by 6 union with 2n pi plus pi by 6 to 2n plus 1 pi. Okay, where n is equal to 0 plus minus 1. So this is the domain. So this thing here is the domain. So as you can see, this is more about trigonometry really than anything else. I don't want sine x to become greater than half. So I have to avoid those values where sine x's value becomes greater than half, or it becomes between half and 1. Okay. So basically from this you can see we want to remove values of x for which sine x exceeds half. So when you remove those values, you get this domain. So the concept of this question is simple, but the application was a little bit lengthy and tricky. So I'm working out the solution for you. Now we'll discuss about the range also.
So,
Yes.
so how did that -1 come up?
How did that?
-1 come up.
Because sine x is anyway not less than -1 no, for all values of x. When we say that sine x is less than equal to half, that means it's only between minus half and 1 and half. No? You're following, no?
Yes, sir.
Sin x is never less than -1. No? Sin x in general is between -1 and 1. But here we want to avoid values which are greater than half. So we'll take only between -1 and half. So you can see we want sin x to be between this value and this value, -1 and half. But we want to avoid this part between half and 1. So for that, we have to take the domain like this. The general solution of the domain will be like this. In the first cycle, 0 to 2 pi, it will be like this. From 0 to 30, and then again in union with 150 to 360. You can also think of this like this, that x belongs to 0 to 30 degrees, union with 150 degrees to 360 in the first loop, in 0 to 360. That's why when we generalize it, this 2n pi concept comes in. So this is clear. Now let's come to the range. Now for range, we have to look at maximum and minimum value of y, and that's pretty simple. So for range of this function, okay, we have to see that y's minimum value will correspond to square root of this thing's minimum value. Now 1 minus 2 sin x, what is the minimum value it can have? It can have a minimum value of 0. for sine x equal to half or x equal to 30 degrees, 150 degrees, 390 degrees, so on and so forth. Okay. So minimum value of y is 0. And similarly, y's maximum possible value is square root of 1 minus 2 sine x, this thing's maximum value. Now 1 minus 2 sine x, this one's maximum value will be 3 for sine x equal to minus 1. That is x equal to 270 degrees or minus 90 degrees, so on and so forth. Okay. So y's maximum value is root 3. So y in general cannot be less than 0 and cannot be greater than root 3. So the range is belonging to the set 0 to 3. So that is now the complete solution of this.
So,
Yes.
so in the above one, we saw that x can also be 0 degrees, right?
Yeah, x can be 0. No?
So, sir, in the minimum value, in 1 minus 2 sine x, there should be 0 also. So,
नहीं, 0 minimum नहीं होगा बेटा. Because see, when is this function minimum? When sine x is maximum, no? It's 1 minus 2 sine x, no? So 1 minus 2x sine x का minimum value क्या होगा? When this 2 sine x term is maximum, no? So the maximum value of this sine x that we can take is half, no?
Yes, sir.
Understood? And similarly, the minimum value of sine x is minus 1. So when sine x is minimum, that is when y is maximum, no? Because y is like square root of 1 minus 2 sine x. So we are subtracting sine x, no? 1 minus 2 sine x. So when we take sine x minimum, we get y maximum. When we take sine x maximum, we get y minimum. Got it, no?
Yes, sir.
So y's minimum value is when sine x is maximum. Okay. And similarly, y's maximum value, that is when sine x is minimum. Now the minimum value of sine x we can take here is minus 1, but the maximum value we can take is only half. So if we take more than half, then we get a square root of negative quantity, so y is not defined. Okay, Ansh, so to answer your question, what is the concept we are applying behind calculation of domain and range? Here, for the given function, we have to find the domain, means we have to find all values of x for which y is defined as a real number. So here y is defined as square root of some expression. So y is defined as a real number only when that expression is a non-negative number. So inside the square root, whatever expression we have, in this case 1 minus 2 sine x, okay, y is real only for such values for which that quantity inside the square root 1 minus 2 sine x should not be negative. It should be greater than equal to 0. So such values of x are called the domain. So that means we can take values of x for this function only which are lying in this set. Because only for these values of x, y will be defined as a real number. And as far as range is concerned, range is the lower limit, that is the global minimum of y to the global maximum of y. So to find the range, we have to find the minimum possible value of y and then the maximum possible value of y. And the range becomes the set of all values of y between this minimum and maximum.
Okay, sir. Thank you.
Sir,
Okay, so
sir, that
next
range
I will move on to.
0 comma root 3, right? In that range.
Sorry, I can't hear you, but I have to speak louder.
Sir, in the range, y belongs to 0 comma root 3 should be there, right?
Sorry, yeah, root 3. That's correct. Please make a correction here. This is root 3. Yes, please make a correction, all of you. This is not 3. This should be root 3. As you can see here, y cannot exceed root 3. So that's approximately 1.7. Root 3 is approximately 1.73. That's correct. Okay. Okay, next up I'm going to do question number 1 part 3. Now this is, in this question the treatment will be slightly different because we are dealing with the sum of two trigonometric terms. So we will have to make use of local maxima and minima for the range. Okay. So let's understand this question. Yeah, so one thing we can see is that sin x and cos x are defined for all real numbers. So there's no problem with the domain. We can see that cos x is defined for all real x and same for sin x. Okay. So therefore, cos x plus sin x will also be defined for all real values of x. So therefore, domain of the function is very simple. Domain of the function will become x belongs to all real numbers. Okay. But about range, now if we think about range, what we can understand that cos x is periodic. Okay, and it ranges between -1 and +1. Sin x is also periodic and it also ranges between -1 and +1. So therefore, y will also be periodic. Now we don't know as yet what the maximum value of y will be and what will be the minimum value, but it will be periodic in nature. That means it repeats, okay, in cycles of 2 pi, because this has a cycle or a period. Okay, and so does this. So overall, y will also be periodic. So the moment we understand y is periodic, so therefore we can say that local maxima of y will be its global maximum. Okay. And local minima of y again will be its global minimum. Okay. And these will repeat in cycles of 2 pi. So therefore, all we need to do to calculate global maxima and minima is we need to find the local maxima and minima in one cycle of 0 to 2 pi. Okay. So hence what we need to do here is to find range okay, we just need to see the local maxima for one cycle, that is x belonging between 0 and 2 pi. So that is one effective method we can go with. Okay. So far I've just described the method for the range. Now let's implement that method. So this will give us a good practice of local maxima and minima concept also here. Okay. So now the problem has changed. To find the range, what we need to do is for this function, we need to just find the local maxima and minima. Okay, so remember the 3-step process that we have done. Step 1, we need to find the domain, the derivative and the second derivative. So dy by dx, we can see, differentiate this. It's cos x minus sin x, and second derivative, differentiate this. So that is minus sin x minus cos x, or we can say minus of sin x plus cos x. Okay. Then step 2, we need to find the critical points So what are the critical points? They are points at which the derivative is 0. So cos x minus sin x should be 0. So cos x should be equal to sin x. Okay. Now that we know happens at two places, pi by 4 or 45 degrees and 5 pi by 4. Okay. Because at so general solution x is equal to 2n pi plus pi by 4, 2n pi plus 5 pi by 4. Okay. So basically in first and third quadrant, sine and cos are of same sign. So basically you know that sine pi by 4 is equal to cos pi by 4 is equal to 1 by root 2, and sine 5 pi by 4 is equal to cos 5 pi by 4 is equal to minus 1 by root. So using that concept from trigonometry. So we have in the fundamental cycle of 0 to 2 pi, we have two critical points. And in general, we have infinite critical points because they repeat. So here n is equal to 0 plus minus 1. Okay. So these type of questions involving trigonometric relations, now you can treat them more like trigonometric questions of maths actually. Okay. But we will see that we require this kind of analysis in some chapters in physics in future, which is why it's very important that you learn to do this kind of analysis here. Okay. So now step 3. So our critical points are which? So critical points are x equal to pi by 4 or 45 degrees and x equal to 5 pi by 4 or 225 degrees in one cycle. Okay. In one fundamental cycle. Of course, there are repeated values. I'm not getting into that again. Okay, now step 3, we need to do the second derivative test. So at each of the critical points, so let's start with pi by 4, the value of second derivative, that is d2y by dx square at the value of x equal to pi by 4. So that is how much it is, minus of sine pi by 4 plus cos pi by 4. So you'll see that is a negative value. Okay. So that means that implies that the function has local maxima at x equal to pi by 4. Okay. Similarly, when we analyze the second point, 5 pi by 4, we will see that it has a local minimum. So now we have found at which points the function is having local maxima and local minima. So we'll put those values of the points back in the function. Okay, so remember what was the function? Y was sine x plus cos x. And from that, we will find the local maxima and the local minima. Okay. So I'm just leaving you some time to go through these steps. And if you understood up to here, complete the steps for the second critical point also, second derivative test. And from that, calculate the value of local maxima and minima, please, for this function. Yes, Per, very good. That's correct. Your answers are 100% correct for this. Okay, so repeating the same test at second derivative test, again repeating it at x equal to 5 pi by 4, you will see that the value of the second derivative will come out to be plus root 2. So it will come out to be a positive value. So which means that y has a local minima at x equal to pi by, sorry, at x equal to 5 pi by. Okay. So now we come back to the function. So our function y is equal to fx is sine x plus cos x. Now this has a local maxima at which point? At x equal to pi by 4. Okay. So what is that local maxima's value? The local maxima's value is the value of the function. It's the y coordinate of the function at x equal to pi by 4. So it is sine pi by 4 plus cos pi by 4, which is plus root 2. So the local maxima, its value is plus root 2, and where it occurs at x equal to pi by 4. And similarly, it has a local minima at the point x equal to 5 pi by 4 or 225 degrees. So that will come out to be minus 1 by root 2 minus 1 by root 2. That will be minus root 2. So the value of our local minima is minus root 2. And it occurs at this point. So now we can see that because the function is periodic, therefore our range is limited to this. It does not come below minus root 2, and it does not go above root 2. The values of y are like this. And of course, x we have seen belongs to the set of all real numbers. So that becomes a critical analysis of this particular function. Okay, so hope this is clear. So let's pick up another example of a trigonometric function. So now in this one, I'm going to outline the steps and I would like you people to try out yourself. Okay. The fifth part. Now see, here also we can understand that it's a periodic function. So local maxima and minima will be global maxima and minima. But we can also see that we can convert this to a quadratic function in sine. Okay. So we can also make use of that. Anyhow, so again, you can see that x belongs to the set of all real numbers. But cos square x and sin x are periodic, okay, with respect to x. Cos square x ranges between 0 and 1, and sin x ranges between -1 and 1. With a cycle of pi for cos square x and cycle of 2 pi. So therefore, what we can see is that y will also be periodic. So therefore, y's maxima, that is global maxima, will also be its local maxima. Okay, within the cycle of 0 to 2 pi. And similarly, y's global minima will be equal to its local minima within a cycle of 0 to 2 pi. So the same method you can use over here also to execute this. Okay. Yes, very good, Perf. That's correct. So try it out by this method, or alternately, you can also use another method. You can convert this into a quadratic function in sine also. So alternately, okay. So you can also write this as like this. So you can write it as 5 plus sin x minus 1 whole square. And from this also you can understand. So you can see that this term that you have over here for all real x, okay, sin x is between -1 and 1. Therefore, sin x minus 1 whole square is between 0 and 4. So therefore, y is between 5 and 9.
So,
Yes.
so why is it till 4 and 5 and 9?
Sorry, come again, a little bit louder.
So why the range is still 0 to 0 less than equal to sin x minus 1 the whole square and less than equal to 4?
This one, no? Okay, see, sin x minus 1 whole square, its maximum value is when sin x minus 1 is having a maximum positive or negative value.
Yes, sir.
Okay, so sin x ka minimum value kitna hai? -1.
Yes, sir.
Understood or no?
Yes, sir.
Okay. Just a minute, I'll share the file again. Just one small correction here. There should be a minus sign in between. This is 5 minus of. So it's basically, we can write this as 4 plus 1 minus like this. So next step, we can write this as so this is 5 minus of 1 plus sine square x minus 2 sine x. Okay, so that's how it becomes this. So accordingly, the range will be between 1 and 5. Because this whole term is ranging between 0 and 4. Okay, so therefore y will have a minimum value when this sin x minus 1 whole square is maximum, that is 4. So 5 minus 1, 5 minus 4, 1. It will have maximum value when this term is minimum. So this term's minimum value is 0. So it's 5. Okay. So according to this method that I've shown you over here, the range. So this is a rather easy method. This moment I'll share again. Yeah. So this is a rather easy method here. That y belongs to the interval 1 to 5, including both the numbers. Closed interval 1 to 5. Okay. So we were able to do this. So this is more like a algebraic manipulation kind of method. But we are able to do this because we noticed that you can write the function as a quadratic in sin x. If that had not happened, then we would have been forced to use maximum minimum. That is the concept of local maxima and minimum. So actually for this question, you can go with this alternate method only. You can later try out this maximum minimum method also, and you can verify the answer with that, but you can go with this method for now.
Sir.
Yes.
Sir, actually, I tried this sum with that local maxima minima method.
Yes,
So
but
we got a case in which the double derivative was 0.
You got a case where double second derivative is coming 0, kya?
Second derivative, yes sir.
Okay. I will tell you a method of what to do when second derivative comes 0. Okay, we'll discuss later about that.
Okay sir.
But you are getting this value of range now, 1 to 5 using that also.
I'm getting the same answer.
What are the critical points you are getting?
Sir, critical points, sir, where y prime is 0, sir, at x equals to pi by 2 and 3 pi by 2.
Pi by 2 and 3 pi by 2. Okay, so when you substitute those values, you will see you will get 1 and 5, right?
Yes.
Okay. Only thing is your second derivative is also coming out to be 0. So when
Yes.
that happens, we have to apply a more more advanced method for understanding local maxima and minima. Which point is local maxima and which point is local minima. Okay, but see, one thing you can always do is you can go back to the number line analysis, that where the function is increasing and where it is decreasing. So that will tell you why at the point pi by 2 you are getting a local maxima, and at 3 pi by 2 or minus pi by 2 you are getting a local minima. You following, Parth?
Yes sir, yes sir.
So if at this stage you can do like this, that if your second derivative is not giving you the indication because it's neither positive nor negative because it's 0, that means you can always go back to the number line method and see the analysis of the derivative, that it should be rising, the function should be rising up to one critical point and then dropping after that. So that one is the local maxima, and for the other one it should be dropping and then rising. So that one is the local minimum.
Okay sir, understood.
Okay, now I want to come to some examples of question 2. I mean, some of the cases of question 2. Let's do that. So that is directly asking you for local maxima and minima. So in question 2, we don't need to do the analysis of domain, range, and all these things. Okay. So let me start with the second part. So this was an interesting. Yes.
Sir, in the first part, like it asked us to find the domain and the range. So, sir,
Yeah.
so we can use local maxima and minima for as a fixed thing to find the range and the domain.
No, beta, देखो क्या होता है ना, that if we have a certain function which does not have a local minima or does not have a local maxima, then the global maxima and minima does not have any correlation with it. Na? It's only in the case of periodic functions that the global maxima is also local maxima.
So, sir, is there any fixed thing to find the domain and the range? Either it is
Yeah, so that's what I told you. Na? The general definition of domain is the same which we have discussed, that it is all values of x for which y is real. So we have to analyze that accordingly. And the general definition of range is the maximum possible value of y and minimum possible value of y, all values in between those. So we have to actually do the analysis of that thing. Got it now?
Yes, sir.
Okay, so let's do the second part of question 2. Y is equal to x square plus 1 by x square. We want to find the local maxima and minima. So we will go with a 3-step process here. So step 1, find the derivative and second derivative. So if you differentiate this function, you can see you'll get 2x minus 2 by x cube. Okay. And if you differentiate this once more, you'll get the second derivative, which will come out to be 2, right? Minus 2 into minus 3, so that's plus 6 into x to the power minus 3 minus 1, so x to the power minus 4. So this is our second derivative. Okay, and this is our derivative. So now second step, we need to find critical points. So our critical points are the points at which the derivative should be 0. So notice the point x equal to 0 is not included in the domain of the function, though we don't need to worry about that here. But we should take all values of x other than 0. So this x cube in the denominator doesn't really create too much of a problem for us. So we can take 2 by x cube common, and we'll have x to the power 4 minus 1. So further we can write that as 2 by x cube into x square minus 1 . So our critical points will be x equal to 1 and x equal to minus 1. So we are getting two critical points. Now this is a very interesting case because one generally thinks that if we have two critical points, one of them must be local maxima and one of them must be local minima. But here that is not going to be the case. Okay. So it's one of those unique functions. Anyway, so don't worry about that. We will discuss why that happens in just a bit of time. So our two steps are done. Now let's come to the third step. Let's analyze the second derivative's value at each of these. So you can see at each of the critical points, what is the value of second derivative coming out to be? It's coming out to be 8. Okay. Because you have x to the power 4 here, so it doesn't matter whether it's plus 1 or minus 1. So it's positive. That means these are both which type of points? They are local minima type of points. So very strange situation here, and I'll discuss why that is happening. So step 3. Second derivative test. So first we can see at x equal to 1, the value of our second derivative is 2 plus 6 by 1 square. So that is a positive value. So that means the function has a local minimum. At x equal to 1. And again, let's do the test at x equal to minus 1. That's also a positive value. So interestingly, we're getting something very strange, that both our critical points are having local minimum. So at this stage, our question is almost over, but it still leaves the question, how come this is happening? So we'll do a bit more analysis to understand how come this is happening also. Okay. But as far as this particular question is concerned, now all we have to do is that we have to understand that fx has local maxima equal to what? F of 1. So that is 1 square plus 1 by 1 square, that is 2, at the point x equal to 1. So the value of the local maxima is equal to 2 at the point x equal to 1. And similarly, it also has, local minima, my mistake. This is not local maxima, this is local minima. Both the points are giving us minimas. It has a minima of this much, okay. And fx again has another local maxima, another local minima, my mistake. Remember, there's no restriction on number of maximas and minimas, so there's no problem that we are having multiple maximas and minimas. So again, it has a local minima equal to f of minus 1, which is again interestingly equal to the same value also, equal to 2, but at this time at the point minus 1. So two separate points, both are giving the same value of local minimum, which is equal to 2. So as far as this question is concerned, the analysis is over. What the question asked is find local maxima and minima. So the analysis is over. Now based on this, what we can say is that for this function, there is only local minima, there is no local maxima. And the value of the local minima is equal to 2 at both the critical points. So the conclusion here is that the function x square plus 1 by x square has local minima equal to 2 at x equal to 1 and x equal to minus 1. And what we can say about local maxima does not exist for it. The graph of the function should be such that it does not have any peak point. It has two dip points, but no peak point. Now you might wonder how this is happening. Okay, it appears very strange. So I will show you that also. But as far as this question is concerned, what we were supposed to do according to the language of the question, we were just supposed to find this out, and that's done. Okay, so I will just take you through the steps above also once. Okay. So the 3-step process, okay, step 1, step 2, and step 3. Okay, Vinith. Sometimes that can happen. Okay, but with more experience in mathematics, you will learn to analyze these things yourself. So if you reached up to this point and got the solution, it's a very good thing. Right? Okay, so these are some of the tricky questions that I'm teaching you just for the sake of experience over here. Generally in physics, on an everyday level, we don't have to analyze such tricky things. It will be simple quadratic functions, cubic functions, polynomial functions of the type, the other questions in the sheet, or so you'll see that they are easier than these. Okay. But even in these, the steps are the same. It's just that each step is lengthier. The maths involved in each step is lengthier. Now, let's actually analyze why this happens in this function. So if you observe one thing very interesting here, that this function is what we call an even function. So an even function means that the powers of x are only even. So the value of the function at some plus a is equal to the value of the function at minus. So for example, the value of the function at plus 2 is how much? It is 4.25. The value of the function at minus 2 is also 4.25. The value of the function at 10 is 100.01. The value of the function at minus 10 is also 100.01. So one thing we can see. Okay. So that's one observation that we have. And the second thing is that for x equal to 0, y is not defined. Okay. So the domain of the function is basically minus infinity to 0 union with 0 to infinity. But for x tending to 0, what about the value of y? Y tends to infinity, because 1 by x square, that term tends to 0. And similarly, for x tending to infinity, again y is tending to infinity. X tending to minus infinity, y is again tending to infinity. Okay. And add to this, we have local minima equal to 2 at x equal to plus 1, x equal to minus 2. So if you put together this information on the number line, you can see that the point 0, this has to be removed from our domain. Okay. But we have 1 and minus 1 as very critical points. Okay. Now the function goes to infinity as x tends to infinity. Okay. It goes to infinity as x tends to minus infinity. Okay. And then again goes to infinity as x tends to 0. And again goes to infinity as x tends to 0. But it has local minima equal to 2 here and local minima equal to 2 here. So this is why this happens. Okay. So the number line analysis also brings a lot of clarity to what is happening to the function over here. And you can support this with the derivative being positive and negative also. But that I've not done, it was not required over. So with the help of all these tools, now you can see that you can come up with quite an accurate graph of the function also. And of course, all the question marks about the function, that why it behaves in this way, is finally answered by looking at the detailed graph. So it's a very interesting function in that sense.
So can't we say x tending to 0 is the global maxima?
Yes, global maxima is infinity. So it is both at x tending to 0 as well as at x tending to plus minus infinity. But it is not a local maxima point. So local maxima, as far as that is concerned, it does not exist. There is no peak point. When we draw the graph, we will see there is no peak point in the graph. But there are two dip points. Okay. So as far as the question was concerned, we were asked to comment about local maxima and minima. So about local maxima, our answer has to be that it does not exist. Global maxima, you're correct, it's infinity. So that way you can see the range of the function is from 2 to infinity. Okay, closed interval 2 to infinity. The function never has a value of less than 2, but it can go up to infinity. So domain is all real numbers other than 0. Range is 2 to infinity. Local minima, there are these 2 points. Local maxima does not exist. So that will be the complete detailed workup about the function. So you realize that the function has a very symmetric kind of graph because it has that property of being even. That is, the value of the function at any positive x is the same as its value at the corresponding negative coordinate. So the graph of the function will look something like this. And this side, it will be just symmetrical. So it will be like a mirror image. A proper, well-drawn graph, these should be exactly symmetrical. See that. So its domain, we can say, is the set of all real numbers excluding 0. Its range, we can see, is 2 to infinity. Local maxima does not exist. Local minima, its value is 2 and it occurs at x equal to plus minus 1. Okay. Now we'll pick up one of the algebraic functions which was a little bit challenging. Actually, I'll discuss third and fourth both. Even this one requires a bit of analysis. We want to find local maxima and minima. So let's go over a step-by-step process again. So derivative of the function, when you differentiate, you should get minus 2 cos x sin x plus sin x, or you can also write this conveniently as minus sin 2x plus sin x. And second derivative, for that it is more convenient to differentiate this one. So you'll see it is minus 2 cos 2x plus cos x. Now second step, to find our critical points. So for that we have to find the roots of this equation dy by dx equal to 0. So now we will see that in this either sin x should be 0, that means x is 0 pi, or in general solution n pi, where n is this, or 1 minus 2 cos x, sorry, minus should be 0, or cos x should be 1 by 2. So in fundamental cycle, x is either pi by 3, that is 60 degrees, or 4 pi by 3. Oh, sorry, 2 pi minus pi by 3. So that's how much? 5 pi by 3. Cos is positive in first and fourth, that is 60 degrees or 300 degrees. General solution, we can write x is equal to 2n pi plus minus pi by 3. But right now we'll stick to more about the fundamental domain, I mean fundamental cycle of 0 to 2 pi. So that is these two values and these two values. So we are getting 4 critical points in all. In that 0 to 2 pi fundamental cycle, our critical points are 0, pi by 3, right, pi, and 5 pi by 3. And then they repeat in cycles of 2 pi. So we need to check the second derivative test at 4 points. Yes.
So they repeat the cycle again and again repeats. So we can say that the cycle can go to infinity.
Yeah. See, the domain is -2 plus infinity. No? So there are infinite critical points here.
So,
in a
so
cycle of, sorry,
why are we restricting the domain?
because we are not restricting. What we are saying is that it will repeat, na? So we don't need to repeat the analysis. But whatever is happening at the critical point 0, same thing will happen at 360, same thing will happen at 720. So we don't need to take all those infinite points. Na?
Okay, sir, got it.
You understanding that? So to find the local maxima and minima, we just need to find the analysis for these 4 critical points, because this is what is happening between 0 and 2 pi. Now the same graph, the same thing will repeat between 2 pi and 4 pi. Then again, it will repeat between 4 pi and 6 pi, or on the negative side between minus 2 pi and 0, or between minus 4 pi and minus 2 pi. So we don't need to analyze the infinite points. We just need to analyze in one cycle. Okay?
Yes, sir. समझ गया.
Okay, so now let's come to the second derivative test for each of these. So 4 points we need to check. At each critical point. So first let's check x equal to 0. Second derivative's value at x equal to 0. Now see, above I've written what the second derivative is. It is minus 2 cos 2x plus cos x. So it is minus 2 cos 0 plus cos 0. So that's how much? That's minus 1. So it is negative. So that means there is local maxima at x equal to 0. Then second point we'll check is pi by 3 or 60 degrees. So second derivative's value will become minus 2 cos 2 pi by 3, because it's 2x, okay, plus cos pi by 3. So cos 120 is minus half. So this will become minus half into 2, that's into minus 2, that's minus 1. Sorry, plus 1 plus cos 60, that's half. So it's positive. So that means we have a local minima at x equal to pi by 3. Okay. Now like this, I want you to check the other 2 points also, and you will see that in sequence, they are again maxima and minima. So basically what is happening, the function is having a maxima at 0, okay, then it's having a minima at 60, then again having a maxima at 180, then again having a minima. So it will be like this. So you can check that out with the calculation. So this will be a sequence of points. In order, there will be maxima, minima, maxima, minima, like this. And then it repeats in cycles of 2 pi. So like I've confirmed for the first 2 points, you can confirm for the second and for the third and fourth point also. So try to complete this analysis yourself. I'll put up the answers in a moment, and then you can find the local maximas and minimas also. Yes, very good, Parv. That's correct. Your answers are 100% correct. Okay, so hope you have worked this out. It's a little bit time consuming, but you learn a lot about trigonometry and maths equations involving trigonometry. And you will see in future chapters in physics, this kind of analysis here will help you a lot. So anyway, so the value of the second derivative at pi will become minus 2 cos 2x. So that will become 2 pi. Okay. Plus cos x. So that's cos pi. So that will become minus 3. So again, that is negative. So again, as expected, we are getting a local maximum at x equal to pi. And finally, the fourth point, 5 pi by 3. So it might be more convenient to write this as minus pi by 3, but I will go with this only. That will become minus 2 cos 2x. So that will be 10 pi by 3. Plus cos x, so plus cos 5 pi by 3. So I'll work out the value here for you. Okay. So this 10 pi by 3, now we can write it as, can be written as 3 plus 1 by 3 pi. So that is equivalent to 2 pi plus pi plus pi by 3. So that is equivalent to pi plus pi by 3. So therefore, cos of 10 pi by 3 is equivalent to cos of pi plus pi by 3, which is minus cos pi by 3. Third quadrant, right? So it's minus half. So again, this will become minus half into minus 2. So that's 1 and half. So it's positive. So again, we will get a local minimum at x equal to 5 pi by 3. So now remember what our function was. Our function was cos square x minus cos x. So this function has at x equal to 0, we have a local maxima whose value is f0. So you'll see that is cos square 0 minus cos 0, which is 0. So this is our local maxima at the point x equal to 0. Now next, at x equal to pi by 3, we have a local minima, which is the value of the function at pi by 3. So that's cos square pi by 3 minus cos pi by 3. It's minus 1 by 4. So the value of the minima is minus 1 by 4. It occurs at the point pi by 3. So if you try to visualize the graph of this function, you see it has very interesting kind of behavior. Goes from 0 to -1/4, then goes up to 2, and again comes back to -1/4. Then this cycle repeats. There's this kind of a so you can also see that this function has a domain that belongs to all real numbers. And from this, you can also understand that its range is between -1/4 and 2. Though this was not asked in the question, but what was asked, that part is completed over here. Local maximas and minimas. Okay, people, so hope this analysis is clear. Now, one more question. I just wanted to discuss the general method and values. Is the fourth part of the second question. This just involves some extra lengthy calculation. Otherwise, it's pretty simple. So again, the differentiation. So here the differentiation is the thing that is lengthy. You have to use the quotient rule. So denominator into differential of numerator minus numerator into differential of denominator. So denominator's differentiation is done by chain rule, as you can see, divided by denominator square. So this is 1 plus x square to the power 3 by 2 minus 3x square into 1 plus x square to the power half divided by 1 plus x square to the power 3. So further simplifying, in the numerator, you can see we can take 1 plus x square to the power half common. So we are left with 1 plus x square minus 3x square upon 1 plus x square to the power 3. And also we can, these are common factors. So numerator will become 1 minus 2x square and denominator can be reduced to power 3 minus half, so power 5 by 2. So this is our dy by dx. So this is the lengthy step here, and of course second derivative is also going to be lengthy. So second derivative, we have to differentiate this. So same method, denominator into differentiation of numerator, that is minus 4x minus numerator into differentiation of denominator. The whole thing divided by the denominator squared. So once again, you can see that we'll be able to take something common over here. This will become so we can take 1 plus x squared to the power 3 by 2 common. So we'll be left with minus 4x into 1 plus x square minus 5x into 1 minus 2x square. So when we solve out the numerator, you can see we have minus 4 minus 5. So that is minus 9x. Okay. And minus 4x square plus 10x square. So plus 6x square. 5 minus 3 by 2. So that's 7 by 2. So it is basically like this. It is 3x, 2x minus 3. So both these are a bit of gigantic calculations. But once we have done with this, the rest part is quite simple. So step 2 and step 3 are quite easy. So I would encourage you to try out those steps yourself, find the critical point and do the second derivative test. You'll see you'll get a quite simple kind of result after this. This was a task that was a bit daunting in this, finding the derivative using the quotient rule and then finding the second derivative. again using the quotient rule and a lot of simplification algebraically. So just go over these steps and then find out the critical points. Step 2. So you'll see that's quite easy. And then do the second derivative test. That's also going to be quite easy. So just to save a bit of time, I'll just put the values here. So x equal to 1 by root 2 and x equal to minus 1 by root 2. These two will be our critical points. And when we do our third step, we will see that second derivative at x equal to 1 by root 2 will come out to be positive, which means that the function, will come out to be negative, which means that the function has local maximum at x equal to 1 by root 2. And second derivative at x equal to, so these steps are a bit lengthy, but to work them out, at x equal to minus 1 by root 2. So when you work the values out, you will see that the function at 1 by root 2 has a value of 2 by 3 root 3, and the function at minus 1 by root 2 has a value of minus 2 by 3 root 3. So this is the local maximum, and this is the local minimum. So I will send you the solutions with the detailed steps and all for all these questions, including question 3, 4, and 5 also. All the other parts that we haven't done in class today. But I would encourage you to go through these questions that we've done, go through the methods carefully today. And any questions you haven't attempted earlier, try them out tomorrow, okay, or whatever time you have left today, and then only go through the solutions that I've discussed. Now, in the interest of just moving ahead in syllabus, I'm moving on to integration. Okay, if there are any doubts pending, we will come back to those questions again in the next class. Okay? So don't worry about that. But let us begin the second part of calculus, which is integral calculus. So this we will find much easier to understand because we are already familiar with one part of calculus. So there are two types of operations in integral calculus. The first type of operation is called indefinite integration. So this is an operation which applies to a function again and calculates its antiderivative. So let us understand the meaning of the term antiderivative. If differentiation of this function is equal to fx, then we say that this ix is the antiderivative of fx. Okay, but how do we go in the forward direction? So this is calculated by applying integration to the function fx. Okay. So this is just the definition. Just make a note of it. So for example, we can see that differentiation of the function x squared plus c, where c is any constant, is 2x. Okay. So that basically means that x squared plus c is the antiderivative for the function fx is equal to 2x. Is the antiderivative. Is the opposite process of differentiation. Okay, now the symbol for integration is like this. This is called the integration symbol or the indefinite integration symbol. Okay. So it is applied to a function in this manner. So this is now going to be read as indefinite integration of the function fx. Okay. But the dx is there over there to tell us that it is with respect to the variable x. So for example, if I say I have integration of n dt, so it is understood here that n is a function of the variable t. Okay. And this whole thing is the integration or indefinite integration of n with respect to t. Now this operation results in giving us what is called the antiderivative. Which further implies that differentiation of this quantity that we get will be equal to fx.
Sir, can you zoom out a bit? So I missed some of the upper part. Sir?
Yes.
Sir, can you zoom out a bit? I missed some of the upper part.
Sorry, little bit louder, please.
Can you zoom out a bit? I missed writing some of the part
Yeah,
that is about this.
So just like we had seen that differentiation is an operation that gives us derivative. Okay, so if we think of differentiation as an operation like this, so if we input a function fx, the output that we get is the derivative. Okay, so this is the derivative. Like that now, integration is something where if we input a function fx, the output that we get will be the antiderivative of that function, which we generally denote with a symbol capital I, because it comes from integration. So that now brings us to our first formula of integration. This is actually very simple, that we know that differentiation of x to the power n is given by the formula nx to the power n minus 1. Okay. Or we can say that differentiation of x to the power n plus 1. Suppose I take the value of n as n plus 1. So this will be n plus 1 into x to the power n. So now I can also say that if I divide both sides by n plus 1, so this quantity Okay, 1 upon n plus 1 times the derivative of x to the power n plus 1 is x to the power n. Okay. So I can say that derivative of x to the power n plus 1 upon n plus 1 is x to the power n, and since differentiation of a constant is equal to 0, so we can generalize this and say that differentiation of this kind of a term is equal to x to the power n. So that means that antiderivative of x to the power n equals to x to the power n plus 1 upon n plus 1 plus c. That is, if we take this as our fx, then this is our ix. So this gives us our first formula of integration. This tells us that integration of x to the power n with respect to x is given by the formula but for n not equal to minus 1. Is valid for all values of n other than minus 1, because with minus 1 the denominator will become 0, so this formula will give us an undefined value. So this is the basic formula for integration of algebraic functions. So this comes by differentiation. So this comes by integration. This is the antiderivative. Okay, so we'll also discuss about what happens if n is equal to -1, but this is the first important formula for us in integration. So one thing you can understand that the antiderivative of any function fx always has a constant term c, which can have any real value. So that is why it is called, so basically Ix, it is more a family of functions. So that is why it is called indefinite integration, because the answer is not a definite value. It is a family of functions. So for example, using this formula, we can see that the integration of x will be x to the power 1 plus 1 upon 1 plus 1 plus c. So that means it's x square by 2 plus c. Okay. Now this c could be any real number. So basically it could be x square plus by 2 plus 0 or 1 or 100 or minus 100 or 1 by root 2, any such real number value. So basically there are infinite functions which satisfy the condition of being the indefinite integration of x. And those infinite functions are represented by a family which we can say is x square by 2 plus c. So that is why it is called indefinite integration. It does not give us a definite answer. It gives us an indefinite answer, but in the form of a family of functions. So that is pretty useful on its own. So for example, integration of root x. So same way we have applied the laws of indices and all that to differentiation, only the formula changes. That is 2 by 3 x to the power 3 by 2 plus. So you can see that if the function is root x, then the antiderivative of the function is 2 by 3 x to the power 3 by 2 plus c. And we can understand that differentiation of this function will give us the original function we had integrated, because it's the antiderivative. Now also alongside, let us note down the special case. So remember here n should not be equal to, so it is valid for all n other than -1. For n equal to -1, we have the formula. It is natural log of x plus c, because we know that differentiation of ln x is equal to 1 by x. So therefore antiderivative of 1 by x is ln x plus c. So this is like the exception to this formula. This is a general formula, but with the exception that n should not be -1. And when n is -1, you should remember this special case or this exception. Okay, now as we wind up very quickly, we'll just see there are the basic properties of integration. Yes, Jitesh, that's correct. Integration is not an operation that can be applied to any and every functions. There are certain functions which are called non-integrable. That means they are not antiderivative for any particular function. But at this stage, we will not worry about such complicated things at our, basic calculus level.
Sir, can
We
you
will.
scroll up a little, please?
Sorry, what was the doubt, Madam?
Sir, can you scroll up?
Yeah.
Please, I missed some part.
Yeah. This part, huh?
Yes, sir.
Yeah.
Thank you, sir.
Okay. So very quickly, we'll just see two basic properties of integration after having seen the formula. The three properties. If we integrate a constant, it gives us a linear function. So k is a constant. So for example, integration of 5 will be 5x plus c, because you can see that differentiation of any linear function of the type 5x plus any constant is 5. So this is the first property. Okay. Then the second property is integration of a constant multiplied by a function, very much like differentiation. The constant comes out. So for example, if we are doing integration of 3x square, so we'll bring the 3 outside and then we'll use the x to the power n rule. So 3 into x to the power 2 plus 1 upon 2 plus 1 plus c. So as you can see, this will become x cubed by x cubed plus c, 3. And you can check that differentiation of x cubed plus c is indeed 3x squared. And finally, the third property, which is similar to distributive property that we had seen for differentiation. So using these three properties, we can integrate a very large variety of algebraic functions, including polynomial functions, but also non-polynomial algebraic functions. So for example, we want to integrate something like x square plus 4x cubed. So this will become integration of x square plus 4 times integration of x cubed. So x cubed by 3 plus 4 into x to the power 4 plus by 4. And we will write a combined constant, because there's two separate integrals would have given us one constant each, but we will add them and write that as a combined constant. So this will become x to the power 4 plus x cubed by 3 plus c. So you can see that this thing is the antiderivative of this. If you differentiate this term, we'll get what we have over here, which is x square plus 4x cubed. Okay, so with that, we complete the first lesson of integration also, the very basics of indefinite integration. Okay. As a couple of you have pointed out in the text messages, integration also has to do with area under a curve, calculation of area under the graph of a function, but that is called definite integration. So that is the second type of operation which we'll learn about in the next lecture, which is called definite integration. This is the first type of operation which is called indefinite integration. And in indefinite integration, we just calculate what is called the antiderivative of a given function. So antiderivative means it is such a function whose derivative is fx. So antiderivative of fx is ix. That means ix's differentiation is fx. So it's the reverse process of differentiation. And that is why it has the constant of integration. Always to remember. Okay. So needless to say that this is eventually going to be an important part of your maths syllabus also. But as of now, we need the basic concepts of integration along with differentiation for physics. So we study all this under basic calculus. Okay? So that's it for today's session, people. Wish you all the best. I will send you the notes and the recording along with also the hints and solutions of the worksheet 5.
Okay.
Yes.
Sir, do we have any specific value for C?
No, the thing is the value of C is not specific. No? It can take any real number value from minus to plus infinity. That is why it is called indefinite. You understanding the point?
Yeah, but sir, will it be given or we have to assume?
No. See, value of C will have to be calculated from some other condition that you know about the function.
Okay, sir.
Okay. Yeah. The upcoming major test will have the portion of complete application of differentiation plus basic part of integration. That is what we've discussed today. That basic.
Okay, sir.